we say from memorizing. It's more about if you know, 3.5 is specifically for OC, something single bonded to oxygen or this is where benzene hydrogens show up. That's a much better practice because then eventually you won't need a table because you know where approximately they show up. But I understand in the beginning, of course, you might want to keep these handy so you can use them. Okay, so, excuse me.
You have a lot of papers right now.
Okay, here's a compound. Everybody ready? Question number 1. Proton. We are still on proton, so only proton. How many proton signals do you expect this to show?
3.
Does everybody agree? 3? Is that a yes?
Yes.
Yes? Let's see how, where. Do you all agree that these 3 are homotopic with each other?
Yes.
Yep.
These 3 are homotopic with each other?
Yep.
But then these 3 and these 3 are also identical because you can rotate about the single bond. Everybody agrees?
Yep.
That these 6 are equivalent?
Yeah.
Yep.
But then there's another hydrogen right there which is totally unique. No other hydrogen like it, so let's call it B, yes?
Yep.
And then these 3 are homotopic with each other, so they'll give 1/3 signal. Everybody agrees?
Yep.
Questions?
Why didn't we do the double bond?
Hydrogen, is there any hydrogen on that?
Oh, so
We're talking about proton NMR spectroscopy,
My bad.
which means we're only looking at H-NMR.
Sorry.
H's.
Good question.
There are
I had no idea.
hydrogens there.
Okay.
Yeah?
Thank you.
Everybody okay? Yes.
Why are A and B different from C?
Well, those are attached to carbon, those are attached to oxygen. Completely different from each other. You see that? Anything else, guys? Okay. Next question. Same thing, give me integration. What's the expected integration ratio? So again, let's go A to B to C. What do you expect? What do you expect the integration for A to be equal to?
9, 7.
It's equal to the number of hydrogens responsible for that signal. So how many hydrogens are contributing to signal A?
6.
6.
How about B?
1.
And C?
3.
That's your range?
6 to 1.
I thought I was saying.
Louder?
Oh, sorry, I was struggling because I thought A and B were on this, you were talking about the same group there.
Oh, so sorry. Yeah, I wrote them kinda together. B is this guy right there. Yeah. Okay, third thing. What about expected multiplicity? Oh, we haven't done that yet. Sorry. Sorry, we haven't done that yet. Okay. Expected chemical shifts. Let's talk about that. Expected, again, these are expected values based on what we know. So where about do we expect signal A to show up? So these are sp3 hybridized hydrogens on an sp3 hybridized carbon. They're attached to carbon, no double bonds, no oxygens, no nothing there. So where do you expect these guys to show up? About 1 ppm or below. They can even be less than 1 ppm. That's where they show up, right? Please, if you look at your tables, the simple CH3 is proton NMR table. That's carbon NMR. Proton NMR, please. That's where they show up. Do you guys remember that line thing I drew?
Yep.
Yeah.
Everybody with me? Yes? Okay. Where do we expect signal B to show up? Please notice it's attached to a CO, double bond O. Where do they show up?
2.0.
2.0. But then do you guys remember how I said everything being the same, excuse me, CH3 will be smaller ppm compared to methylene group, which is smaller ppm compared to methine group. Yes? On your table, a CH3 which is attached to a C double bond O is expected to be around 2.0 ppm, isn't that right?
Yeah.
So a CH2 attached to a C double bond O will be slightly higher than that. So again, I'm really approximating, maybe 2.2-ish, maybe 2.1, 2.2, maybe 2.3, we don't, but a little bit higher than that. We good, everybody? So what do you think you would expect if there were a methine that is connected to double bond C double bond O? A little bit higher than that. So maybe, again, I'm totally approximating that maybe it's 2.4, maybe it's about 2.5-ish, so on and so forth. That's kind of the approximation we are making. Does that make sense to everybody?
Yeah.
So I'm just saying maybe again 2.2 to 2.5, because again, exactly you can't predict, but it will be in that area of the spectrum. Everybody with me? Because it's attached to a C double bond O. What about C? Signal C. It's the carbon is single bonded to oxygen. Where do we about see those? So once again, if there's a single bond CH3, where do we expect to see these? Again, we drew out a chart last week, right? With the approximate ranges.
Yes.
Where does that show up in that chart? Do you get? They're about 3.5, exactly. CH3 is 3.5. If it were an OCH2 something, that would be maybe 3.7. If it is an OCH, that might be 3.9, 3.0 or 4.0, something like that. The CH3 is around that. So I expect this CH3 to be about 3.5 ppms. Does that make sense, everybody?
Mm-hmm.
You guys want me to draw that chart out again? Because it seems like everybody seems to have misplaced that chart. Again, the exact number is not a very important thing, not very useful to know. It's more useful to know about where to expect different kinds of signals to show up. That's what we really need to focus on. So do you want me to draw that again? Because we really need to be familiar with that.
I would like to.
I have it, but it's hard to read because of the circled H's.
Well, those are the H's we are focusing on, but that's not the chart I'm referring
Yeah,
to.
no.
Well, I'm referring to the chart that we drew out using
I lost mine.
the other handout I gave you with approximate
Oh, that one.
ranges.
Yeah.
Do you guys remember this one?
Yeah.
Yes? Do you want us to draw that again?
Yes, please.
Please, okay, so let's do that again.
And I can
It's,
help.
again, very important for us to know the important areas of the spectrum to expect different kinds of signals, because you can't spend 30 minutes looking for a number. That's not very useful way of spending your time. You need to know, oh, this is where I should look if there's a specific thing you're looking for. So for proton NMR, this is only for H-NMR.
Oh, yeah.
What's the range of the spectrum? Oh, thank you so much, Mark. Appreciate it. 0 ppm to about 14. Doesn't really, actually even 13, but sure, let's just put it, nothing really. What's at 0? Does anybody remember? How do we mark the 0?
Tetramental silent.
TMS, exactly. We mark it. So that's 0. Okay. Now, starting from here, so, bless you. An ordinary, bless you again. An ordinary, normal hydrogen on an sp3 hybridized carbon shows here. Nothing when they're attached to other carbons. So alkane, so to speak, hydrogens show up here. Now once again, remember, everything else being the same, methyl is lower than methylene, which is lower than methine. That always applies. Then I personally like the two part ppm area. This is the area where very specifically either a benzylic CH3 will show up. CH3 also means CH2 also means CH. I'm writing CH3 just for simplification. But again, as I've already said, CH3 will always be lower than CH2, will always be lower than methine. But in that area of the spectrum, so benzylic shows up there, and if you have C double bond O bonded, then those will show up here. The reason I'm circling those hydrogens is because those are the hydrogens that we are focusing on.
Okay.
The others will be every other places.
Yeah.
Then 3.5, I really like that part of the spectrum because very specifically the ones attached to oxygen, single bond oxygen show up. So again, very, very important, very useful area of the spectrum. Then comes 6.5, so maybe 5 point, and these again, a little bit wiggle room is always possible. So this is the area where vinylic hydrogens show up, meaning hydrogens on an alkene double bond. 6.5 to about 8 is very specifically for benzene hydrogens. Hydrogens on the benzene ring, those show up there.
Does it have to be carbon for the, like the?
Yeah.
Oh, so okay.
Yeah.
Sorry, just
Which one?
like the one with the double bond, C, like that one.
On the carbon, yes, an alkene.
Okay.
Alkene is with
Yeah,
carbon-carbon
yeah.
double bond.
I just want to make sure. Thank you.
Okay. Then comes 9 is very, very specifically for an aldehyde hydrogen. That shows up there. 10, very specifically for a phenol hydrogen, not phenol, phenol. Phenol is this guy. So that hydrogen shows around 10. And then anywhere from 12 to maybe even 14 again, very rare to see those, but carboxylic acid hydrogen proton shows the most downfield, the highest ppm values. Now I'm missing a couple here, OH, NH, and the alkyne hydrogens. So alkyne hydrogens in this region, this is where hydrogen on a triple bond will show up. Now OH and NH actually can have a very broad range because of hydrogen bonding. They can be anywhere in this range. Alcohol OH and or amine NH can be anywhere in that.
So
range.
would it be big?
No, these are actually not like IR, how OH is broad in IR. These are broad, but they will probably not be big because of integration. It's all about integration. IR is not quantitative, NMR is very quantitative.
Okay.
Were you going to say something?
I was, but then I'm not. So you're good.
Sure?
Yeah.
Okay.
You said here for it's phenyl and it's
Phenol.
not phenol. Okay. What's the difference? I don't.
That's the name of the molecule.
Oh,
called
not
alcohol.
phenyl. Phenol.
Phenyl. Phenyl is a group, as you already know. Phenyl is when you have a benzene ring attached to something else that, isn't that what we
Yeah.
call it?
Yeah.
So different things. The OH of phenol shows around 10 ppms, but the hydrogens on the phenyl ring, on the benzene ring, show in that range. So it's important for us to know the ranges, guys, because it's not a very good use of time if you are fishing a huge table in front of you and then you're trying to find, that's not going to help. That's actually going to create panic. It's more important to remember, oh, this is where we see that, and this is where we see that, so that makes your search a little bit more efficient. Sounds okay, everybody?
Yeah.
So does that fit? Expected? I love silence.
Yep.
Not really. Yes,
It's all right.
it's all right.
What do you mean by expected?
That's where we expect those signals to be on the spectrum. We expect the chemical shift of these hydrogens to be 3.5 ppm. We expect the chemical shift of this hydrogen to be there, we expect the chemical shift B signal to be there. That's what, I'm not sure I understand your question.
When you say number of signals, I'm sorry, it means ages.
Well, if you're studying H-NMR, what else would
H.
it be?
Yeah.
I'm a little confused with the questions
I'm
now.
sorry, it's because I'm a little lost,
If
but
we're
I
studying
was.
H-NMR, we're looking at H's.
Yeah.
We're not
No, that's what I
studying
thought. I
anything
just
else.
want to make sure those are the signals.
Yes.
So, wait, I think I just solved my own question.
What was the
But,
question, in case someone
so-
else is thinking?
So you have like R bonded to C, sp3, and then an H. If you have other organic compounds, would those also just be R's, and it wouldn't matter, it would just be the C to the H?
So ours is a very general way of us representing anything made of carbons and hydrogens. It's a very general thing with zero detail in there. Is that what you asked?
I was thinking like if I had a phenyl attached to an sp3 carbon, and then I had like another.
Then will that, okay, I think I understand your question. Let me know if that's not, if that's what you mean. Let's say you have sp3 carbon, hydrogen, and hydrogen, blah, blah, and then there is something else there.
Yeah, like
Which
another
may
thing that's on the
be-
table.
Which may be, I'm just making stuff up right now. Let's say an aldehyde group.
Yeah.
So will the position of these be affected by both? The answer is absolutely. Absolutely. So will I, if again, we are digressing here, but if I needed to predict where those protons will show up, I will have to factor this and factor this as well, because those hydrogens are being affected by both. So in reality, when, and this is beyond us, we are not going to get to that level of detail, there is actually a mathematical calculation we can do that, okay, this much effect from here and this much effect from there, so where will it we expect to see it? We are not going to do that. But the simple answer to your question, Dash, is absolutely, absolutely. I would not expect those hydrogens to be here. I'll probably expect them to be more D-shielded or higher ppm values because they're being affected by both of those groups. Is that the question you were
Yeah.
asking? Yes, absolutely. Anything else, guys, before we go forward? Okay, so do you all agree with this, what we wrote here?
Yeah.
So if I asked you this compound that's on the board versus let's look at this guy. How many proton? We're talking about H-NMR, so let's not please get confused with all of that stuff. It's just proton NMR. How many signals do I expect to see for this molecule? Louder?
2.
Why two?
I still see 3.
This tells me
Oh,
nobody
yeah, three,
has
three.
actually
I
done
still-
any
I still
work
see
over the
3.
weekend.
3, my bad.
Three, same as that. These are identical.
Yes.
This is on its own. And C,
Yeah.
same.
It's just back.
Agreed?
Correct. My bad.
Integration, what would be the expected integration for A?
6,
How about B?
3.
Same.
Uh-huh.
So how would I use proton NMR to differentiate between the two? What will be different
ppm.
between the two molecules? They have the same number of signals, they have the same integrations, all of that is same. So how would I be able to say whether the spectrum belongs to this compound or this? By the way, what's the relationship between these two compounds?
Structural isomers?
Do you all agree they are structural isomers? Right?
Yeah.
So how would I be able to tell which of these two structural isomers the proton NMR spectrum belongs to?
Oh.
What will help me differentiate between the two?
The spectrum.
So be more specific than that, Dash.
Like based off the chemical group.
Shifts,
Yeah.
chemical shifts. What were you saying, Jasmine?
I said chemical.
Same thing,
Yeah,
right?
same thing.
Exactly. So what will be different here? Can you tell me what will really be useful to us, which will help us differentiate where they show up? So do you all agree that this signal B is expected around there?
Yeah.
Yep.
Where do you expect this signal to show?
Oh.
Signal?
3.5.
That's connected to C double bond O.
Oh.
This is
Oh.
single
Single.
O.
Correct.
Where would you expect this guy to show up?
3.5.
But probably more because
3.6.
remember methyl, methylene, methine, right? Methyl is smaller ppm than methylene, which is smaller ppm than methine. And that's a methine. So probably almost 3.94 ppm or so and so forth.
Can we still say 3.5 or no?
I would prefer that you went a little higher because CH3 is lower than CH2 is
Okay.
lower than CH. Are you guys with me?
Yeah.
Yep.
So notice, pretty big difference.
Yes.
What about this methyl group? Here we expected it around 3.5 because it's direct bonded, single bonded to oxygen. Where would you expect that guy to be?
9.
CC double
Not
bond.
9, please. Let's look at the table and then say it. Where would you expect this to show?
9.
CH9.
2.0.
It's a CH3 guy. We've forgotten.
C
2.0.
2.0. 2.0.
Do we need a couple
Oh
of
yeah,
few
2.0.
seconds of breathing and then regroup? Is that okay? We can do that, but we cannot go back to 2 months ago. Can't
2.0.
do that. Someone said something.
2.0.
2. That's a CH3 direct single bonded to C double bond. Oh, this is around 2 ppm. Like that.
Correct.
So the point is, depending on where you see those signals, you'll be able to identify whether it's this compound or it's this compound. Are you guys with me?
Yes.
Yep.
So I'm curious, why 9? I'm still not pretty much following.
I
just-
didn't read my spectrum right.
Oh, were you thinking that's a H?
Yeah.
Oh, so then is that what you were thinking
Yeah.
as well?
That's what
Yeah.
But it's not, it's a
CH
CH.
double
Yeah,
bond.
I noticed.
Perfect. So let's be careful.
Sorry.
Is everybody following this so far? Yes?
Yep, sort
I
of.
have a question.
Yes, please go ahead.
So, would you get the 4 ppm again? Because it's a,
So I'm starting with this base value. Starting with that base value. It's basically a carbon hydrogen direct single bonded to oxygen, right? If these were all methyl, if this were a methyl, we would expect that to be 3.5, right?
oh,
Three.
But
okay.
if it is a methylene, everything else being the same, where do we expect them to be? Slightly higher than
Two
this.
H's.
Approximately 3.7, right? But that is a methine.
1H.
So that should be even higher
4.
than that. So I approximated it. Maybe it's 3.9, maybe it's 4. You wrote 3.9, I'm okay. You wrote 3.8, I'm okay with that. As long as you recognize that starting with this base value, we went a little higher because that is methyl. Does that make sense? Vincent, do you see that? Yeah? Anybody else?
That's good.
Okay. Let's try another one. How many signals? Let's start with that. How many signals do we expect? And again, we are talking about proton. How many signals do we expect?
Wouldn't it be 3?
No.
1. So here. Oh, here's
How
2.
many signals do we expect?
Here.
No. 6.
Double checking. Is there a stereo center? I don't see a stereo center. Is there?
I don't know.
Frick. I don't see one.
Okay, then how many signals do we expect? 3? No. 5?
I'm thinking 4.
Yes.
Oh, wait, no, it's 5. Yeah, yeah, no, it was
5.
No, I was totally looking at.
Let's see which
I was
5.
looking at the oxygen connection.
Oh, yeah.
Let's start from here.
Okay.
Do you
1.
agree? A?
Yes.
Do you agree? B?
Yes.
Those are enantiotropic. These because as you said there's no stereocenter. So those are enantiotropic.
Yeah.
Do you agree that these two are identical?
Yes.
Do you
Oh.
agree these two are identical?
Yes.
And then of course let's not forget that guy. All H's show. All protons. Is that what you were thinking when you said 5? Everybody okay?
Yeah.
Okay. Now what about the ratio? Integration ratio. So let's start with A. So what is A? 3. B?
2.
C?
That's
C is 2.
4.
D? 4. How 4?
Well, I added.
What does this circle inside mean?
Pi bond.
So then how do you get 4?
My bad, my bad.
Let's not forget what we've already learned, guys. D? E?
1. D is 2.
Everybody okay with that? Now let's project expected chemical shifts based on where they're supposed to be. I'm going to start with A. Where do we expect A to show up? Signal A to B.
1.0.
About it, because there's really nothing special about that carbon. It's an sp3 carbon attached to another sp. There's nothing. It's like an alkane. We good? Everybody?
Yes.
How about B? Now notice it's exactly, please notice it's a single bond oxygen. So the base is 3.5, but this is a methylene. So maybe
3.8.
a little bit higher than that, 3.5. We okay, everybody?
Yep.
How about C and D? We are not ready to break them, but where do we expect both of them to be?
So that'd be like 8.
6.5 to 8 ppm. Now, depending on which is more de-shielded, we can talk about it. Maybe we should talk about it. Give me a second. But they're both, all of these are attached to the benzene range. So that's the benzene range. Everybody okay? Yes? How about E? Where do we expect that hydrogen to show up?
HO.
HCO2. HCO2.
What is that group CO2H?
Carbonic, some sort of acid, whatever the acid is. That one thing.
So where does that show up?
At the very end.
Okay, there we go.
That's carboxylic acid.
My eyes weren't looking.
So that's about 13 or so ppm. Those are our expected placements of the. Are you guys with me?
Yes.
Everybody okay? So again, as I've already said, please don't focus on memorizing these tables. You can't. It's not, and plus it's not useful to do that. What's more useful is for us to be familiar with where different signals show up, hopefully through practice, so that you're not looking for a value, you're actually looking at the area of the spectrum to find what we're looking for. And we will do practice, but just keep that in mind. Okay, so coming back here, I just have to draw it all over again. So you guys correctly said that, let me just draw it again. Right? You guys correctly said that these hydrogens are equivalent, so they'll give us one signal. And these are equivalent, give us a different signal, right? Everybody, you're absolutely right. My question is, which one, the red A or the blue B, do you expect to be more downfield? Do you guys remember the terms downfield and upfield?
Yeah.
Yes, Josh.
Is this red?
Oh, give me a second. What do I mean by downfield?
I don't know.
More towards 14, right?
Yeah.
And up, what do we mean by upfield? More
Yeah.
towards 0, exactly. Which hydrogens have higher ppm value, de-shielded or shielded?
De-shielded.
meaning the electron density has been pulled away from them. They have a partial positiveness to them. And if the hydrogen is shielded by electron density, those are towards the low ppm value. With me, everybody?
Yeah.
So coming back, my question to you is, which one, the red A or the blue B, do we expect to be more downfield? Meaning higher ppm, they are in this range, absolutely, but which will be closer to 8? That's the question. You said which one? Dash.
I said the red would be.
Why?
Because it's attached, so you follow a carbon, and then it's attached to the carboxyl group.
So?
So that carboxyl group is a much higher ppm, so.
Oh wait, that has nothing to do with it. Your answer is probably right, actually, not probably, it is, but not because of that reason. Why?
The oxygen's right next to it.
So you're saying blue is more de-shielded? And, okay, so what if oxygen is right next to it, so what?
It's very electronegative.
So what is it doing?
Going
But
more
it's
towards
pulling
the
through pi bonds or sigma bonds?
Sigma bond.
What is that called?
Inductive effect.
Inductive effect, right? Yes?
Yeah.
How many of you agree? I don't. I'm not saying you're wrong, Eric, in terms of what oxygen is doing, yes, but actually oxygen is doing one more thing, which we are not remembering. Does oxygen have lone pairs?
Yes.
So if it has lone pairs, what is it also going to do?
Give.
Give away some electrons.
Isn't that allylic lone pairs?
Yeah.
Yeah.
A little
So what will
resonates.
it do? Starts with the letter R.
It's resonant.
Can't forget resonance. So is it going to push electron density into the benzene ring or away from it by resonance? Will go into the ring.
Darker there.
So is that making these hydrogens, the blue hydrogens, electron rich or electron poor just by resonance, guys? Forget about the inductive for a moment. By resonance, are those blue hydrogens getting more electrons or less electrons?
More.
Is that shielded or de-shielded? Which is stronger, inductive or resonance? Always. If ever resonance and inductive effect are pointing in opposite directions, resonance wins. Inductive effect is a much weaker effect. So, the other thing is, what about this guy? Can it also not participate in resonance? Look, there's a pi bond conjugated. Can we push electron density out this way by resonance? What does that do to the red hydrogens? Does it take electron density away from them or give them electron density? Didn't hear that enough. If the resonance is going away out of the ring towards the carboxylic acid groups, what is that doing to the hydrogens? Is that making these hydrogens electron poor or electron rich?
Electron poor.
So will these be de-shielded or shielded?
De-shielded.
So which one, A or B, is more downfield? Oh,
A.
exactly. You would expect the signal, the red signal, to be higher ppm value and the blue signal to be lower ppm. Okay, blue. Pretend that's blue. Both black, blue start with the letter B. The point is, you have to consider when you're looking at structures is, okay, which direction is electron density going in? Because lower electron density around hydrogens, higher ppm values, higher electron density around hydrogens, they are more shielded, so lower ppm.
Can you repeat that? I want to write that.
What did I say? The more de-shielded hydrogens, meaning they have lower electron density around them. So lower electron density around hydrogens, higher ppm values. Higher electron density around hydrogens, lower ppm values because they are more upfield. So it's all about how much electron density there is around the nucleus of hydrogen atoms. Does that make sense, everybody? Did you get that or should I write it?
Write it.
I was the only one.
I couldn't keep up.
Lower E density around H's. More this year.
Okay. Are we all good? And when you are considering that, of course, inductive effect matters, no doubt about it. But resonance effect is also something you have to keep in mind. And anytime there is contradiction between the two, resonance wins. Resonance is way stronger effect than inductive effect. So please keep that in mind as well. Yes? Sorry. Okay, go ahead.
Please, I'm just
No,
wanting
you're
to
good.
help I understand.
Yes?
So electrons going into so in one way, thinking about this,
Yes.
evidently the wrong way,
Go ahead.
is you got electrons going into the benzene ring and you got electrons going out of the benzene ring.
Right. But who's pulling
Why
or pushing
is there a
strong?
winner and loser?
Say again?
So why is there a winner? So you got electrons coming in, you got electrons going out.
Okay, got it. So
In-
let's say you are pulling me with one of my arms, and then Iman is pulling me with opposite direction with my other arm, but you pull stronger, who wins?
I
That's
do.
the idea.
And so I should see that side as
Stronger. Exactly. There's a net shift of electron density because of resonance in this direction. Out of there, going here. And if you draw out the resonance structures, and
That
one
makes
of the
sense.
ways to figure that out also is to just draw the resonance
Explain.
structures and see which one ends with negative charges,
Because
which
of
one ends
resonance.
with positive charges. That will automatically then
O,
tell
like
you,
the-
oh, the one with negative charge falls in
Like
this
the pair-
category, the one with
Pair
positive.
stuff, right? Serious? We're doing resonance. We're
Make
taking
sense,
it to the other
everyone?
side. So it's going over.
Okay,
Does that make
cool.
sense?
And
So,
is that one, why is that one
number
stronger?
of proton signals,
Because of the resonance.
inductive effect.
Because it's
Oh,
pulling,
sorry.
but it's
Integration ratios, chemical shifts. What was the fourth thing about proton NMR spectroscopy? Multiplicity, also known as coupling. And again, we are not getting into the physics of this technique. We are really looking at its application. So without going into the physics part of this, okay, let's start with this example. How many proton signals do you expect for chloroethane? Sorry, louder?
two. Two?
Oh, sorry.
Two signals?
Do you all agree?
Yes.
Two signals? So do you all agree that this is A, this is B?
Yeah.
Yes.
What integration do you expect for A and B?
3 to 2.
A to B should be 3 to 2, right? Approximately, which one do you expect to be a higher ppm value, which means de-shielded? Which one do you expect to be lower ppm value, meaning more shielded, relatively?
B is more de-shielded.
Sorry, could you say that again, Karna?
B is more de-shielded.
Do you all agree?
Yes.
So again, by how much and all, we're not interested in any of that. We just because that's now this is inductive. There's no resonance here because it's not resonance is not possible. So this is purely inductive effect of chlorine. So we expect B signals to have a higher ppm value. May I just randomly say, okay, that's 0. So B is for 2 hydrogens, let's say, and then that's for 3 hydrogens, let's say. And of course, you got a little blip for TMS. Okay, everybody? Yeah?
Wait, I have a question. Might sound dumb, but are we doing it by electronegativity, like the
I don't understand that question, Iman.
like?
I mean,
we
in this
said
case,
B is more deshielded, whatever.
well, so in this example, what else could there be? Can we have resonance in this example? Is based
Yes.
on the rules for resonance, is
No.
that possible?
No.
Because we have pair bonds.
No,
in
there's
the-
no-
You can't. That's SP3. This is SP3. For resonance, we require parallel unhybridized p orbitals. Do either of them have unhybridized p orbitals? So can we have resonance?
No.
So then what is the only criteria here?
Inductive effect.
Chlorine's electronegativity, which means it's pulling electron density
Yeah,
through
that's
that
what
s-
I meant.
This is inductive effect.
Thank you.
So again, will that be the same for every molecule? No, you gotta look at the structure and then decide, oh, this or that, so on and so forth.
Yeah, thank you.
So that is why the hydrogens on B are more de-shielded compared to A because of chlorine pulling electron density. Are you guys with me? Everybody? Okay. Now, if I ran a proton NMR for this compound, that's not what I will see. What I will instead see is that the signal for B, same area, meaning integration that you expect because it's two hydrogens, but it's split into 4 parts. Signal for A, same area because that's for 3 hydrogens, but that signal is actually split into 3. So what I will actually see is as follows. What I will see, this signal, and I'm really bad at drawing, so I apologize ahead of time, but this is going to be split into 4 parts. And we'll talk about why and how in just a second. And this signal, so same chemical shift, that doesn't change. This signal will be split into 3 parts. Same total area, but now split into same chemical shift, doesn't change, but the signal area is now split into a certain number of parts. That is called multiplicity. And the reason why that happens is because the magnetic field of one hydrogen, the magnetic field created by the nuclei B, are actually going to be affected by the magnetic field created by nuclei A and vice versa. That's what coupling is all about. These hydrogens will be affected by those, and these hydrogens will be affected by those. So that is called splitting. It's also, by the way, called splitting, multiplicity, whatever term you want to give it. So, the formula is a signal for a certain kind of proton, and we'll do examples, is split into n plus 1. Where n is the number of neighboring hydrogens. Or I should actually use the word adjacent because we don't want to go too far away. We're not looking at long range coupling. Neighboring hydrogens. Or hydrogens on adjacent carbons. Generally speaking, 3 sigma bonds away. Okay, so when we are looking at this molecule, let me draw it out again. We all agreed that, yep, it should show us 2 signals because there are 2 kinds of hydrogens. Yep, the integration ratio should be 3 for this, 2 for that. And yep, because of chlorine, those are more downfield compared to these. But the signal A has 2 neighboring hydrogens, 3 sigma bonds away, guys. 1, 2, 3. So the signal A has 2 neighboring hydrogens. So it's split into 2 plus 1, 3. So that area is very symmetrical splitting actually, and we will see those examples. Very symmetrical splitting of that signal into 3 parts. The ratio is 1:3:1. But again, that's not important right now. The important part is that's split into 3. What about signal for B? How many neighboring hydrogens does this guy have? 1, 2, 3 sigma bonds. How many neighboring hydrogens?
3.
So what is 3 plus 1?
4.
So that's why this signal was split into 4 parts. That is called signal splitting, and it tells us how many neighboring hydrogens does this proton, this signal have, because it helps us create a bigger picture.
Can
Does
you,
that make sense? Yes.
Can you show me the neighborings that you chose? I know you did, but I just want to make sure.
This guy has those neighbors.
Yeah.
This guy has those neighbors. If you're looking at signal for A, come on. Where is the neighboring carbon? Isn't that, how many hydrogens on that carbon?
2.
That's it. 2 plus 1, 3.
Oh.
If you're looking at B, how many neighboring, where is the neighboring carbon?
Right there.
And how many hydrogens does it have?
3.
3 plus 1, 4.
Thank you.
So you're looking at the next carbon and the next carbon on all sides, all sides.
So how much hydrogens it has?
How many hydrogens they have, exactly. N is the number of neighboring hydrogens. Yes,
So if there's another carbon
Yeah,
that's
exactly.
in-
yeah, exactly, great question, let's look at that. Because it's affected on all sides. When you're looking at adjacent, you're just not looking on one side, you're looking at all sides. But before we go there, do more examples, do we understand what this is? Then we'll do more examples. We all good? So every signal in proton NMR is split, divided, multiplied, multiplicity is what we call it, based upon neighboring hydrogens. How many neighboring hydrogens does it have? Okay, so how about how many signals proton do you expect for this aldehyde to show? Number of signals?
1, 2, 3, 4.
Sorry?
4.
4, everybody agrees?
Yeah.
So let's say A, B, C, and D? Everybody okay? What do you expect the integration ratio to be?
1,
2, 3.
Do you all agree?
Yeah.
Approximately, where do you expect the chemical shifts to be? Where do you expect A to show up?
H. Oh, in the aldehyde.
What is the number? About 9 ppm.
9.
Where do you expect B to show up? Again, approximately. Where do you expect B to show up? No, but that's next to a C double bond O. That's next, B is right next to a C double bond O, right? About 2.2 or so, right? Everybody okay?
Yep.
Now, where do you expect C to show up?
It's C and C.
Those are attached to B and D, so where do we expect C to show?
6.5.
There's no benzene there. Iman, those are specifically for hydrogens on benzene. Oh, sorry, those are specifically for hydrogens on an alkene, depending on which one
Alkene.
you're referring to. And that's sp3.
1.2.
Louder, please.
1.2.
Okay, I can take that because you're going by the one value being CH3. So, okay, fine, that's totally fine. What about D?
1.
About 1. And does it mean it's exactly 1? No, it can be 0.9, 0.8, whatever it is, but in that part of the spectrum. We good? Now let's add multiplicity. So we've talked about number of signals, we've talked about integration, we talked about chemical shift. Now let's do multiplicity. Multiplicity is about the neighboring hydrogens, hydrogens on adjacent atoms. So let's start with this guy, A. When you look at the carbon that A is on, the next carbon, how many hydrogens does that have?
2.
So what should be the multiplicity of A? 2 plus 1?
3.
That signal we expect to be split into 3 parts. We call that a triplet. Maybe I'll write those terms a little bit later. We'll get back to it. Okay, so let's go to B now. What about B? It has carbons on either side. What about this guy? Does it have a hydrogen?
1,
What about that guy?
2,
So what is the total N?
3,
So what do we expect to see?
5,
4.
4.
4.
Agreed?
3 plus 1.
Although that's
I mean,
a very
2 plus 1.
simplistic view, 3 plus 1, 4.
Plus 1.
But you will probably not see that because, and we are not getting into this part, guys. In this scenario, I expect the multiplicity to be a complex multiplicity. Is this hydrogen the same as C? Is
No.
A the same as C?
No.
So therefore, is it reasonable for us to assume that AB coupling is not going to be the same as BC coupling? Because C and A are very different hydrogens. The value of the amount of interaction A and B have will not be the same as the amount of interaction B and C have because C and A are different. We agree? So actually what we will end up seeing is something that we call complex multiplicity. But maybe we'll put that aside for now and get back to it a bit later. Yes, Carmen?
When you say 3 sigma bonds away, do you mean like up to 3 sigma bonds away?
Yes.
Okay, so it doesn't have to be exactly 3 sigma bonds away. This can't be any more than sigma bonds away.
In some, and there is one particular case where we will look at more than 3 sigma bonds away called long range coupling, but typically, yeah, that's where we'll stop. There is something called long range, which is more than, but it can be less. It can be 2 sigma bonds away too. For diastereotopic hydrogens, they will couple each other because they're 2 sigma bonds away. So we'll get to that example as well. Yes?
So do you just go to the next carbon, or do you just go any carbons within the 3 sigma bonds?
Any carbons within 3 sigma bonds.
So then wouldn't we include D then?
Is that 3 hydrogen? So you're just looking at the carbons. We are looking at hydrogens on those carbons.
Yeah. We're just looking at
1, 2, 3, 4.
Oh, we're going to the
So hydrogens are coupling with each other. I'm not drawing out the hydrogens, but it's the hydrogens that are coupling with each other. And the hydrogens need to be, for the most part, within 3 sigma bonds of each other.
Okay.
Do you see that?
Yeah.
Now, so coming back, guys. So as you guys said for B, you said 3 plus 1, we would expect that to be 4. But as I said, it's actually going to be more complex than that because AB coupling is not going to be of the same intensity as BC coupling would be because A and C are very different. So you will probably see a complex pattern, more complex than that. But anyways, later on. What about C? So what do we expect for C? Multiplicity. So it has carbon on this side, right? 1, 2, 3 sigma bonds away. So how many hydrogens here?
2,
How about 1, 2, 3 sigma bonds on the other side? How many?
3,
So what should be the expected multiplicity for signal C?
6.
6.
How about D?
2 plus 4, 6.
Should expect to be. Everybody okay? So what this is doing, this is not telling us about the hydrogens that the signal is for. This is telling us the hydrogens around the signal that you're looking at. It's a very helpful piece of information. We all good, everybody? Yes? Okay, certain terminologies to keep in mind as we deal with multiplicities. If signal is just 1, that's called a singlet. Singlet means what? Single, 1, no splitting. And we'll look at examples when that's not possible because there are no hydrogens on the neighboring carbon. Okay. When the signal is split into 2, multiplicity is 2. That's called doublet. Where the signal is split into, and it's a very symmetrical splitting pattern. They will be about the same height. When the signal is split into 3, that is a
Triplet.
4. Not quadruplet.
Quadlet.
Tetra.
No, not really.
Quartet.
Quartet. I don't want to draw anymore. 5. So n plus 1, 1, 2, 3, 4. If n plus 1 is 5, that is called a pentet. Some people do call it a quintet, but most of the times I've only seen pentet written. When n plus 1 is equal to 6, that's called a sextet, not a hextet. Of course, if n plus 1 is 7, that is called a septet. 8, octet, 9. I mean, we don't really see beyond that actually, it becomes complex after that. So certain terms for us to please keep in mind. Are we all okay so far? Yes?
So this is just how many spikes we see.
Yes, for each of those signals. Yes, exactly. So let's go back to the worksheet that I gave you guys last week. I do have a few extra copies in case anybody doesn't have theirs. I do have, but let's go back to that worksheet I gave you guys last week. Let's look at this guy. We've already done parts of this question.
Can you grab me one?
Now the question is, how many signals, by the way? How many proton signals for this guy? 1. What should they, if it's all 1, what should be the multiplicity for all of them? Anyone? 1. Singlets. They will all be, because it is just one singlet signal that you will see, because there's no question of neighboring hydrogens. Are you guys okay? Okay, let's go to the next one. How many signals did we expect to see for this guy? Okay, everybody agrees 3? Okay, are you guys thinking A, B, C?
Yes.
What is the expected multiplicity? Careful, you gotta be slow. Don't be in a rush. Multiplicity for A.
3.
Careful, don't be in a rush.
Oh,
We are looking at the
Oh.
next carbon,
the neighbor?
the neighboring adjacent carbon. Which carbon is the adjacent
B.
carbon to those?
One without.
It's this. Is there any hydrogen on that?
No.
So what is N?
And 0.
So what is 0 plus 1?
1.
Singlet. There is no hydrogen on that carbon that is right next to it, three sigma bonds away. If you're looking at this guy, I mean,
Oh.
that's 1, 2, 3, 4 sigma bonds away. So you're only looking at the carbon next to it. You guys with me?
Yep.
What about B? What do we expect the multiplicity for B to be?
Quartet.
Louder?
Quartet.
Quartet?
Yes.
Everybody agrees? Because it has 3 neighboring hydrogens. What about signal C? What do we expect? It's expected to be a triplet because it has 2 neighboring hydrogens. Are you guys with me? Everyone okay? Yes? Sure? Okay, then let's look at the next one. How many signals was this? Proton signals was this?
4 signals.
4 I heard. Okay, so let's see what 4.
5.
A, B, C, D, B, A? Okay.
That's
So
6.
let's talk about A. What do we expect the multiplicity for A to be?
Or is it just count?
B, B.
No, I mean, neighboring there, those are identical, but you're not adding up together. So, because remember again that 3 sigma bond away policy. So what should the signals A be?
Sure.
What should the signal B be?
Single.
Careful.
Oh, sorry.
So pentet.
See, B has this, which is adjacent, and 3 here. So what should it be?
Sextet.
4 plus 1 is 5, not
5.
6.
Pentet.
Agreed?
Yes.
What about C? What do we expect C? Oh, whoa. That's a lot. Now, if you look at C, C is actually seeing, it's seeing these 3 sigma bonds away, seeing these 3 sigma bonds away, and it's seeing these 3 sigma bonds away as well. Ooh. Well, no, but see, you were adding those, with respect to A, those are too far away.
Oh.
With respect to this A, those are too far away. You can't because there are more than 3 sigma bonds away. But here, all of them are 3 sigma bonds away. So you're looking at all H's that are 3 sigma bonds away. So what is that? 7 plus 1?
8.
Do you agree?
Yes.
Only if they're 3 sigma bonds away. Not if they're more than 3 sigma bonds away. I mean, these A will couple with those, but not with those. Do you guys see that? Everybody okay? What about D? What do we expect the multiplicity for D to be?
Doublet.
It has only 1 next to it. So when you're looking for coupling, you're looking at 3 sigma bonds away.
You're looking at adjacent hydrogens 3 sigma bonds away.
Yeah.
Not including the hydrogens that are attached to the source of the signal.
Yes, not equivalent hydrogens. Absolutely. Okay. I just, before you guys try a few of these, we take a little time to work on a few of these. Actually, let's do the next one together also. How many signals?
3 signals.
I heard 3. So A, B, B, A, C, C. Okay. Multiplicity for A. So see, coming back to the question you guys had about adding up. This A that I'm pointing to, is it going to couple to the 2 hydrogens on B?
Yep.
But will it also couple to the 2 hydrogens on the other B?
No.
No. Right? So you're only looking 3 sigma bonds away. So what do you expect the multiplicity of A signal to be?
Triplet.
Do you all agree?
Yeah.
How about B?
Quartet, what's the Q one? Yeah, that would be quartet.
Right? Quartet. How about C? How about C?
Also quartet?
Which is the adjacent carbon to C? Is there any hydrogen on that?
No. So it's the
So
same.
it doesn't count itself then?
No. Oh, no. If I have the same signal as you, then how can we interact, So no, it's coupling with the next door non-equivalent H's. Yes. Not with each other. We good? Okay, so the 3 sigma bond away rule we will follow. However, when it comes to benzene, we are going to take it a little bit further than that. So, when it comes to benzene, we are going to take the coupling a little bit more longer range than 3 sigma bonds away. So when it comes to hydrogens, different meaning non-equivalent that don't have the same chemical shift. If you have 2 non-equivalent that are 1,2 or 1,3, and please make a note, if you haven't, these are not equivalent to each other. They are not giving us the same signal. They're non-equivalent. So 3 different patterns that we will come across. These do have large coupling. So yes, you will see them couple with each other. Because they are 3 sigma bonds away actually. But when they are 1,3, we will see the coupling, but small. But we will see it. We should consider it. But when they are 1,4 with respect to each other, this coupling can be ignored. It is there, but it's too small for us to see. So we are going to ignore that coupling. So if hydrogens that you're looking at are 1,4, we will ignore them. But if they are 1,2 or 1,3, we will consider their couplings. So what do I mean by this? Let me give you an example. How many signals?
2.
Do you all agree? Everybody?
Yeah.
Okay, so I'm assuming you are saying 2 because these are identical?
Yeah.
And these are identical. What is the ratio, integration ratio of A to B?
1 to 1.
Because it's 2 to 2, which is 1 to 1. Do you all agree?
Oh.
Right? Because there's symmetry, so fine, if you want to write 2 to 2, that's okay as well. Totally fine, but I hope we all agree that it's equal. Okay. Multiplicity. So what do we expect the multiplicity for A signal A to be? So is it going to couple with this? Do you think this hydrogen right here will couple to this hydrogen?
Yep.
Yes?
Mm-hmm.
And that's a large coupling. That's a large coupling.
Yeah.
Do you think this, well, but B is the same and this is symmetry. So whatever you see here is going to be reflected here as well. So you don't have to really go there. So what do you expect this multiplicity for this guy to be?
Doublet?
Oh, hold on. Okay, I'm going to leave it there for a moment. Okay, pay attention. Do you also expect these to couple? Because they are 1,3 with respect to each other.
Yep, they have a plane of symmetry.
But that's a small coupling. So, is it going to be a triplet? Not really. Because 1,2 coupling is big. 1,3 coupling is small. So what we will see is definitely see a doublet because of the big coupling. And then each of those will be split again into a doublet because of the small coupling. So you end up seeing a doublet of a doublet. What does that look like? So assume here's your signal. Assume. First, this is split into 2 equal parts because of the large coupling. And then each of those is split again into 2 because of the small coupling. So what we see is not this, we only see that, which is basically a doublet of a doublet. There's coupling here, there's coupling there too. Yes?
So if it was a triplet signal originally and it had a small one, would that be a
Doublet of a triplet.
Doublet, okay.
Absolutely, it can go in any, and maybe we'll see some of those examples here. Yes. What about B? What would we expect the multiplicity of B to be? So is B coupling with this A? Let's assume this B. Is it coupling with that?
Yeah.
What is it going to be because of that A? Is it going to be a doublet, triplet, what? Okay, but is this B also able to couple with that A?
Yes.
Is it enough distance?
Yeah.
So what would be the multiplicity because of that?
Doublet.
Also a doublet of a doublet. We will see 2 doublets of doublets in that space of the spectrum. So it does become quite complicated as we go through different kinds of permutations and combinations. For benzenes, yeah, we need to please keep in mind 1,4 we won't. We will ignore that coupling. So let's look at the next example. How many signals, proton signals, do we expect to see? Sorry? 3?
I pause a second.
Yeah, sorry.
Shouldn't that be a triplet doublet? Or am I
Which
confused?
one?
The
This
D.
one?
Yeah.
It's not going to couple with itself,
Oh, never
right?
mind. I'm being
Those,
dumb.
no, that's okay. We're all processing through it, so don't worry about that. Yeah, so those are identical, so there's no coupling. But if they were not identical, then yes. And we'll look at some of those examples. Absolutely. So how many signals here? You said 3, right?
Yeah.
A, B, C, B. Did I do that correctly? What is the integration ratio? 1 to 2 to 1. Everybody in agreement with that? Okay, let's talk about multiplicity. Let's start with A. Do you think A can couple with this B?
Yeah, it's 1 free.
And what about that B?
Yeah,
Also.
also
Right?
1 free.
So, and those are identical, right?
Yeah.
So how many neighboring hydrogens does A have?
2.
2.
Yeah.
So what do we expect A multiplicity to be? Can it couple with C?
No.
That's too far away.
Yeah.
We are
that's-
going to ignore the 1, 4. Too far away. We good, everybody? Okay, let's talk about B then. Can B couple with A?
Yes.
Yeah,
Can B couple with C?
yeah.
But do you think BC is the same as AB?
No.
See, BC is way large. It's large coupling.
Yeah.
But 1, 3 is small coupling. So should we see a triplet or should we see a doublet of a doublet? Do you all agree?
Yeah.
Because again, this is very large coupling. This is very small coupling. So doublet of a doublet.
Do we want a small coupling or a?
We don't want whatever the instrument gives, we get. It's not our choice. This is what
Oh.
the instrument will do.
Okay, sorry.
Right? So when you run this NMR spectra for this compound, you will expect to see that.
Okay.
Okay?
That's also how the molecules shape.
How about C? Can C couple with B?
Yeah.
Yep, see,
How about the other B?
No.
How about A?
no.
So what do you think the multiplicity for C will be?
Triplet.
Does everybody understand that? Everybody okay? Yes.
So would the triplet for A be smaller than the triplet for C? Because
Yes.
Yeah. Okay.
Oh yeah. Yes, exactly. What does that mean, smaller, by the way? And again, we are going beyond what we need. I'm just looking at 2 doublets. They're 1 doublet. So when the coupling is small, separation is small. That's indicating a small coupling. And when the separation is larger, that's indicating a bigger coupling. A stronger coupling. I should use the word stronger, not bigger. But so this triplet, the 3 will be farther from each other. This triplet, the 3 will be closer to each other. Absolutely, you'll see the difference. We good, everybody? Does that make sense? Everyone okay?
It's just,
Yes.
like over here, you see large, but they're closer, but I shouldn't go by that. And
That
then
has
small,
nothing to do with
it's got
it.
nothing.
Because they are closer, they are able to couple stronger. Because they are a bit farther, they're able to couple.
Okay,
Their
that-
coupling is weaker.
That clicks.
And since this is so far away, it's too weak.
Got it.
Okay, so why don't we? No, that's good. That's good. Could you guys look at the worksheet again, the one that we were looking at a few minutes ago? And why don't you guys go ahead on the next page? Go ahead, work with each other. Let's jot down the multiplicities for each proton signal. So please go ahead, work with each other, then we will compile the responses.
Wait, isn't it this one?
The multiplicities,
Yeah, flip
couplings.
the page. The next page. Go to the next page.
She's doing that one.
Yeah, we're doing the head scene. I don't know.
Yeah. Okay, let's do it. So we get 1, 2, 3,
Wait, we're doing.
Yes?
4. Do you get 4 signals?
Yeah. Forces.
I had like everything aside from last week's.
I know these are there.
I have that one.
Oh, this one
Yeah, that one and the packet.
is not there?
No, neither.
Okay, I will put them there. Thank you for letting me know. The key is there
It
for
also,
this thing.
it also wasn't on it.
Okay, I'll go check. Thank you, Vivian.
Wouldn't A be, what's it called? Penta or Penta? What did you get for A?
I'm not there yet. So let me count.
B.
N plus 1 equals 1. So what did you get for A?
I got pen, like the 5. Pen.
Yeah, me too. No, 4. Quartet. How do you get 5? Oh, no, and the other. No.
Mm-hmm.
Yeah, how did you get 5?
I don't know, I might be wrong, I'm probably
Yeah.
wrong. But there's 3 hydrogen right here, there's 2, and then there's a hydrogen right here.
But doesn't A count as 1?
What?
A doesn't count as 1?
A counts as 3 hydrogens.
No?
I'm not sure.
I'm not sure either. Let me ask.
No, because that's connecting to the carbon. That's a signal bond that goes to the carbon. You still need another signal bond to get to that. So it's 4. Because
Yeah, yeah.
no, because if we had yeah, you do. Yeah, maybe.
From the main hydrogen, the next one, how many sigma bonds do you go through?
Okay, yeah.
So you have some.
Starting from,
I got 6.
So yeah, he counted 1.
so where's the hydrogen?
1 for A.
I'm not sure. That when she asked me, that's what, when I asked her, she showed me. I don't know. I am not sure.
Which hydrogen are you trying to compare? Yeah, one
Sector for those two.
but it can't be
Basically, equivalent hydrogen.
unless you're looking at benzene.
Okay, so that was, so if it's a benzene.
That's the only exception.
Okay, so that's how I was like, my counting.
So unless there is pi bonds in the middle, you go only 3 bonds, sigma bonds. That's
Okay.
it. But if it's benzene, then yes, we can go a little bit farther.
Okay.